This VODcast is on reactions. It's chapter 4 from the textbook. There are several reactions that we cover in the course, and many of them don't happen in solutions. One of the reasons for that is that there's too much heat needed or released to allow water to be present. So in the case of synthesis, you usually need a lot of heat to get it going. Combustion, you have to give it energy to get it started, and it releases a lot of energy when it's done. And decomposition reactions also require a lot of energy to get going. And also they can all release a lot. So if water is ever involved in a reaction, it's usually a gas. But we also have a lot of reactions where solutions are necessary. So these aqueous solutions are solutions where the substance is already attracted to water, and so it mixes with the water. If it can break up into ions, and those ions with their charges can wander through the solution and conduct electricity, we refer to that as an electrolyte. These ions in solution are surrounded by the polar water molecules, which gives them some stability and holds them as ions in a solution. That process is called solvation. So when the water comes in and surrounds an ion from like a sodium chloride crystal and pulls it away, that is called solvation. If the substance remains together and just has an attraction to water, then this is a non-electrolyte. And examples of this might be sugar dissolved in water, where the sugar molecule itself never comes apart. It's just attracted enough to the water that it stays separated from the other sugar molecules and can wander throughout the water. But it can't conduct electricity. So on the left side is the example of solvation of sodium chloride with water, and you can see how the water molecules have arranged themselves to turn and face their charged side to the ion. So the sodium ions, being the purple spheres here, are surrounded by the negative oxygen end of the water molecule, and the chloride ions, which are the green spheres, are being surrounded by the positive hydrogens of the water molecule. On the right side, you see methanol dissolved, and you can see that the water molecules haven't attracted to any ions, that the methanol has stayed together as a whole molecule, but just by its attraction overall to the water, it mixes and spreads out. When we refer to strong electrolytes, we refer to substances that break into ions near 100%. These are your soluble salts or strong acids, so hydrochloric acid or sodium chloride. These are considered strong electrolytes because you don't have any or very few particles in the solution that are still staying together. Most of them have broken apart into ions, 99.9999%. Weak electrolytes only have a small fraction of that substance dissolved as ions. A good example of this is vinegar or acetic acid, where although the acetic acid is very, very soluble in water and mixes completely, only 1% of them will actually dissociate and make ions that conduct electricity. So you have to be careful not to get confused with strong electrolytes and weak electrolytes and solubility. They are two separate things. The dissociation of the ions in weak electrolytes is related to equilibrium, which we will study significantly in more detail later on in future chapters. Precipitation reactions are what you call double replacement reactions in your previous chem course. It's when an insoluble solid is formed when you combine two solutions. So solubility, by definition, is the amount of substance that can be dissolved in a given amount of solvent at a specific temperature. You have to memorize the solubility rules on page 121. Here they are. So make sure you know this chart very, very well inside and out, because you need to be able to predict reactions and products, and you need to know solubilities in order to do that. And in these reactions, there is an exchange of cations and anions from your two substances in the solution, and that's how you can figure out what your products are, and then using the solubility rules determine whether or not they will precipitate or not. When you're writing reactions, we need to be able to write net ionic equations, because that's all that is really cared about in the end, and that's what AP is going to expect you to write all your reactions as. So when you write an equation with the chemical formulas, we call that a molecular equation, and that's where you write everything as just their chemical formulas. When you have ions, you can break up all the ions and show all the individual ions, and that is called the complete ionic equation, or just the ionic equation. So you can see here we took the calcium chloride and broke it up into the ions. Notice I didn't write the chloride ion as a Cl2 minus. I wrote it as 2 Cl minuses because that's what it actually breaks up into in solution. And I broke up the sodium carbonate into ions. Same thing with the sodium. Notice I put the 2 out in front to represent that I have 2 sodium ions. The calcium carbonate I didn't take apart because it's solid. It's the precipitate, so it isn't ions in solution. It is connected and together. And then the sodium chloride I also broke apart into ions. Then we can look at it and say, well, all the substances that stayed ions on both sides haven't really done anything. We call those spectator ions. So by taking them out, we can then have the net ionic equation, just the leftover ionic equation that shows the changes. So you can see that I took the sodium ions out and the chloride ions out because they were ions on both sides of the complete ionic equation. And so they didn't really change, so we don't really care about them. So net ionic equations is what you want to be able to write every time. Another type of reaction is an acid-base neutralization. So the basic definition of acids are substances that donate hydrogen ions, and the basic definition of bases are substances that accept hydrogen ions. That is the Bronsted-Lowry definition, if you remember that from your previous chem course. When they react and neutralize, they make a salt and water. You have to look at table 4.2 in the book. Here it is. And this lists out all the strong acids and strong bases. So when you're writing your net ionic equations, you write these as completely dissociated as ions. Anything that's a weak acid or a base, you would write associated as a molecule. And then sometimes you have neutralization where it makes a gas, like hydrogen sulfide or carbon dioxide. You're familiar with the carbon dioxide reaction because that would be like the baking soda and vinegar where you make carbonic acid, which breaks down into carbon dioxide and water. The hydrogen sulfide is a common one that they talk about. So your sulfide ion and your hydrogen ion are neutralizing each other. And when they neutralize each other, then you get hydrogen sulfide gas, which is given off. We will spend a lot more time looking at the more complicated acid-base reactions over the next few chapters, and even a little bit in this one when you come back to class. Redox reactions are the last major type of reaction. They're reactions where electrons are exchanged. So one substance will give up electrons, another will gain them. The amount lost and gained has to be equal all the time. The substance losing its electrons, we say, is oxidized because its oxidation number goes up, its positive charge or its charge increases. The substance gaining the electrons is reduced because its charge goes down, right? The more electrons it gains, the more negative charges it has. So we have to assign oxidation numbers to all the atoms in the compounds, and they are used to indicate the substances that are oxidized and reduced. So you'll write out the whole equation, you'll figure out what all the oxidation numbers are for all the substances, all the atoms in the equation, and then you'll compare the oxidation numbers from the two sides of the equation to see which ones went up and which ones went down. And then when we come back to class, we'll talk about how to write the half reactions and demonstrate the whole oxidation reduction equation. What you need to know about how to assign oxidation numbers is any substance that's in its elemental form has an oxidation number of 0. For any monatomic ion, the oxidation number equals the charge that that ion has. Oxygen is always a -2, except when it's a peroxide, which isn't very common. And in that case, oxygen has an oxidation number of -1, since 2 of them have a -2 charge. Hydrogen is a +1 charge when bonded to nonmetals and a -1 charge when bonded to metals. And polyatomic ions have a sum of their oxidation numbers that must equal the charge of the ion. So if you know that a PO4 has a -3 charge, and you know that oxygen has a -2 and there are 4 of them, that's -8. So that means the phosphorus must have a +5 charge. Again, we'll spend a lot of time looking at this in class when you come back. Simple redox reactions are the same as the single replacement reactions that we talked about in your previous chemistry course. The activity series determines which ions can replace which. So you're going to need to become familiar with the activity series, although you'll be given a table for the AP test, which will basically be the activity series with other information on it. So you won't have to necessarily memorize the whole thing. Although in some cases, for quick answers, it's good to have some idea of what it is. And as I said several times, we will look at the more complicated redox examples in class. So here's a simple activity series. This is certainly not all-inclusive, but it's all of the major players, so it's good to have an idea of where some of these are in relation to the others. And here's the macroscopic view of a redox reaction and also the submicroscopic view. So you start with the silver nitrate solution where you have silver ions and nitrate ions floating around and your solid copper, so that's all the way on the left. In the middle now you start to get the exchange where the copper is giving up electrons to the silver. So the copper is going to become ions and the silver then is going to become elemental silver. And this happens because copper is more reactive than silver on the activity series. You can see that silver is down towards the bottom here and copper is not much higher but higher nonetheless. So copper will replace silver. Copper is more likely to become ions than silver is. So the copper gives up its electrons to the silver. By doing that, then the copper has to go into solution, and so in the third picture on the right you can see that the silver metal now is sticking to the outside of the copper or plating out on the copper, and some of the copper ions have left and gone into solution, and that's why the solution begins to turn blue, because now you have copper nitrate in solution. So that concludes our general understanding of reactions, so we will cover more in class.